and welcome to the second lecture of module 4. In the previous lecture we introduced nonlinear algebraic equations, where do they arise in chemical engineering problems, and we started off with bracketing methods. We looked at two bracketing methods. The first one was bisection method and the second one was the Regular-Falsy method. In the bracketing methods, what we used was essentially two initial guesses, XL and XR. We chose the two initial guesses such that they lie on the either side of the true solution X star. We verified that by finding out the product f of XL multiplied by f of XR is less than 0. If that is satisfied, those are admissible initial guesses. And then we used ways to actually get the new solution x of I plus 1. In bisection method, what we did was we started off with a particular length of the chord, we halved the chord at each time instant. In the Regular-Falsy method, what we did was we got the 2 points which lied on the curve, we connected those 2 points with a straight line, found out the point where that particular straight line intersects the x axis. That became our new guess. What we did in Regular-Falsy method is essentially when we get the new guess, we again ensured that that particular new guess bracketed the true solution, and then we proceeded. The methods that we are going to cover in this lecture are the methods which are known as open methods, and they are called open methods because they the solutions do not have to bracket the true solution that we have. Okay. So what I will do is I will do a very quick brief recap of what we covered in the Regular-Falsy method, and that is going to motivate our next method, which is called the secant method. The next method is called the secant method, and we will use the Regular-Falsy method in order to motivate our secant method. Okay. So let us just recap what we did with respect to Regular-Falsy. Let us say we have a curve of this type and we started off with XR and XL. What we did was we connected this XR and this XL with a line, and we found out the intersection of that particular line with the x axis, and then we call that as xi plus 1. Okay. The expression for xi plus 1 that we developed in the previous module was xi plus 1 was equal to XL minus FL multiplied by XR minus XL divided by FR minus FL. I mean, of course you can interchange these as well. As long as you interchange both the numerator and denominator, it really does not matter. The reason is negative, this will be negative of this and the denominator will also be negative of this, and the negative will cancel. So this is what we did in order to get the new guess xi plus 1. In Regular-Falsy, then the next step that we implemented was we checked f of xi plus 1 multiplied by f of XL whether or not it is less than 0. If yes, we replaced XL with XR. If no, we replaced if yes, we replaced XR with XI plus 1. If no, we replaced XL with XI plus 1. So in this particular case, we replaced XL with XI plus 1. So that was our Regular-Falsy method, and we kept repeating that until xi plus 1 was close enough to x of L. Okay. That is what we did in the Regular-Falsy method. The secant method works very similar to the Regular-Falsy method, but the only difference is we do not care whether the solutions bracket the true solution or not. Okay. So xi plus 1 is going to be generated in a very similar way, but we drop the notations xl and xr, we drop the pretense whether xl and xr lie on the either side of the solution. We just start with solution 0 with solution 1 and we keep generating the new solutions, and we discard the oldest solution and retain only the latest solution. What I mean by that is we will replace this particular equation with another equation in secant method, and the generation of the new point is going to be x I plus 1 will be equal to x I minus f I multiplied by x I minus x I minus 1 divided by f I minus f I minus 1. Okay. If you compare it with what we have just written a few minutes ago, if you compare this particular expression with the expression for the secant method, the two expressions are one and the same. The only difference is we do not bother whether that xi and xi minus 1 lie on either side of the curve. They can both lie on one side of the curve, they can lie on either sides of the curve, and it really does not matter because the secant method does not depend on bracketing the solution. Okay. So, let us again draw that same curve that we had drawn previously. We will call this as x1, we will call this as x0, okay, and we will connect them with a straight line. This becomes our x2. Okay. So, now we have x0, x1 and x2. What we did in Regulai-Falsy method, we multiplied f of x0 with f of x2 and decided whether x2 is replacing x0 or x2 is going to replace x1. We are not going to do that in secant method. We are going to discard the oldest solution and retain the two new solutions. So, we have x1 and x2 as the two new solutions, and we will look at this particular point. We will join these two with the same curve, okay, and this is now our x3. Okay. Now, up to this point the Regulai-Falsy method and the secant method were used in the same manner. What we ended up doing was we discarded x0 and retained x2, and our x1 and x2 still bracketed the true solution that we got. This is not what we are going to do in secant method. What we realize over here in secant in this method is x2 and x3 are lying on the same side of the solution x star. In Regulai-Falsy we would have retained x1 and x3. In secant we do not retain x1. X1 is the oldest solution we currently have in the memory. We will discard x1 and stay with x2 and x3. Okay. So, now we will have the 2 points not bracketing the solution. Okay. However, that does not matter, we will still go ahead and draw that particular chord, extend it and see where that particular chord intersects the x axis. This becomes our x4. Now, when we have our x4, we will discard our x2, we will stick with x3 and x4, again draw the chord, and we will keep repeating that until we converge to the desired solution. So, looking at the algorithm for secant method, the first step that we do is initial guesses are to be chosen. Okay. In our Regulai-Falsy method, what we had to ensure was f of x0 multiplied by f of x1 was less than 0 for Regulai-Falsy. No need to check this. Okay. So that's the difference between secant and regular falsy. We don't need to check whether x0 and x1 lie on either sides of the true solution x star. Okay. So that's the initial guess. I'll just erase this because since we don't need this particular criterion, I'll just erase this criterion rather than keeping it on the board and cluttering the board. The next is to determine the how we are going to move forward. That means to use xi minus 1 and xi plus 1 and xi minus 1 and xi to get xi plus 1. Now for although I am repeating myself over here, I will just write it down for the sake of completeness. Okay. This is going to be our xi plus 1. Okay. So initial guess is x0 and x1, xi plus 1 is going to be determined through this particular expression. We verify whether the difference xi plus 1 minus xi is less than some tolerance epsilon. If it is, then our numerical solution is equal to x of I plus 1. If it is not, we increment I and we repeat this process repetitively till this particular condition is met. Okay. So this is going to be the algorithm for the secant method. So let us go back again this time again to Excel and try to see what how secant method is going to work. So now we have seen how the secant method works. The way the secant method works is very similar to regular falsy, except the difference between the secant and the regular falsy is that every time we get x of I plus 1, we replace the oldest solution and not necessarily we are not necessarily bothered whether the solution the guesses are going to bracket the true solution or not. So this was what we did in Microsoft Excel in the previous lecture when we worked with regular falsy. What I am going to do again is just copy the previous lecture, essentially just create a copy of the previous lecture so that I do not have to redo everything, and we will call this as the secant method. Okay. In the secant method, what we are interested is again solving the same problem 2 minus x plus ln of x using the secant method. Okay. And in the secant method, we do not have the concept of xl and xr, instead we have x of I plus 1 and x of I minus 1 and x of I. So this guy is going to be nothing but x of I minus 1, the next guy is going to be nothing but x of I. Likewise, we will have f of I minus 1 and we will have f of I. Okay. So these are the two solutions, the two guesses of the solution that we are going to start off with, and then compute x of I plus 1, f of x of I plus 1, and the product fl multiplied by f of I plus 1 is not needed at all. So we will just delete that part. Okay. And let's go ahead and delete this part also completely, so that we start with almost a blank slate. We will start with the initial conditions that we started off with. So we start off with the two initial solutions, x of 0 is equal to 1 and x of 1 is equal to 4. We calculate f of 0 again same way as we had calculated in the previous lecture of this module, 2 minus B4 minus plus ln of B4, and likewise for f of I is going to be 2 minus C4 plus ln of C4. X of I plus 1, as we had said, was computed using x of I minus 1 minus f of I minus 1 multiplied by xi minus xi minus 1 divided by fi minus fi minus 1. Okay, so this is that particular slope term, this is the f term, and this is the x term at I minus 1. Okay, and it is exactly the same as we have done in the Regula-Falsy method, the computing of xi plus 1 given xi minus 1 and xi. So we have not bothered rewriting that particular formula. Remember, we had just copied that particular formula from our previous case. So again, we do not need f of I plus 1 and the error at and the product f of I plus 1 multiplied by f of I at this stage. We will just move the error over here. So this is all that we need for the secant method. In iteration 2, when the iteration number, when I is equal to 2, xi minus 1 is nothing but x of 2 minus 1, which is x of 1, and if you notice, x of 1 at the previous iteration was this particular value. So we will do equal to this guy. So that is what our x of I minus 1 is going to be when I equal to 2. X of I when I equal to 2 is the x of I plus 1 when I equal to 1, right, because when I was equal to 1, x of I plus 1 is nothing but x2, when I equal to 2, x of I is nothing but x2. So we will write this as equal to x of I plus 1. Okay, and now what we do to compute f of I minus 1, we just drag this over here. To compute f of I, we just drag this over here, and to compute x of I plus 1, we just drag this, and the same way with respect to the error we are going to drag. Okay, and now we select this entire row and drag it again, maybe for a total of 10 iterations, let us see, and yes, so that is the 10 iterations. So that is what we now have gotten, and we see that it has converged essentially in 6 iterations. So we will go ahead and delete this part. Okay. So our error criterion was that the error should fall below the epsilon value was 1 e minus 4. Here the error is 3.7 e minus 4, as a result of which we repeat this for one more iteration and we get 4 e minus 4, and the solution that we get over here is essentially 3.14619. that is going to be the solution using the secant method. Okay. So now if you compare, what I want to do is I just want to compare the results of the Regula-Falsy method with the results of the secant method. So what I will do is I will just copy what we had done with Regula-Falsy method in our previous lecture and just paste it over here just for comparison. I will click on paste special. We only want the values, we do not want the computation. So we will just paste the values over here. Okay. So what we started off, what happened in the Regula-Falsy method is that at all times the new guesses of the solution that we generated were all generated to the left of the true solution x star. As a result of this, xr, that is the right hand solution, remained the same at 4.0 all the time, and it was only this solution that we kept changing with the number of iterations. But if you see what is happening in the secant method, the first solution was dropped, second solution was moved back, and the new solution came over here. In the third iteration, it was the second solution was dropped, third iteration moved here, and the new solution moved over here. In the fourth iteration, the third solution was dropped, the previous solution was moved here, and the new solution came over here, so on and so forth. So what we did in the secant method is to retain only the last two solutions, not the left and right solution, and that is essentially where the secant method differs from the regular falsy method. In regular falsy method we essentially kept the solution such that they bracket both the solutions at any given time. Okay. So that is essentially the way the secant method works. Let us say that our f of x was of this particular form. Okay, we are plotting f of x against x. An example of this particular equation is, for example, if we have x square minus 4 equal to 0. Okay, so this is going to be an example of that. So actually this won't be. So let's just look at the case where x square equal to 0 rather than x square minus 4 equal to 0, and this particular guy is 0, and this curve is going to be essentially tangential to this particular axis. If we look at any point on this curve except for the origin, at all the other points on this particular curve, our basically our f of x is always going to be positive. Why just look at x square equal to 0? We could also look at, say, x minus 1 squared equal to 0. So in that particular case the point 1 comma 0 is the true solution, is the true solution of this particular equation. But any point you take along this particular curve, our f of x is going to be greater than 0 for any point which is not equal to x equal to 1. Okay. So if we will try to use any of the bracketing methods, we will not get any admissible solution, because no matter which 2 points you take on this particular curve, our f of xl multiplied by f of xr is always going to be positive for this particular example. Okay. So no matter what method we are going to use, we will not be able to get starting initial guesses for a bracketing method. However, when we are looking at, for example, a secant method, the secant method does not have any problem in an example of this type. The reason why it does not have a problem is that it does not matter that f of xl and f of xr is going to be positive or not. In either cases the secant method is going to work. There is one problem, however, for this kind of a curve for the secant method, is that if the line joining f of xl and f of xr happens to be parallel, if it is parallel to the x axis, then there is no point at which this particular line is going to intersect the x axis, and our secant method is not going to work. In other words, what do we really mean by the line being parallel to x axis? It's nothing but fi minus fi minus 1 equal to 0. This is when secant or the regular falsy method fails. Okay. However, the secant method will not fail if we have even a slight difference between xi and xi plus 1. So if we have a situation of this type, we can always connect this point. We will essentially get this particular point as the next point, and then we will be able to connect this, we will get this as the next next point, and so on and so forth, and then we can continue and we will end up reaching the solution eventually. Okay. So this is what we'll end up getting, and using a secant method. The secant method will still be able to employ to a problem of this sort. However, the regular falsy method we will not be in a position to employ in an example like this. Now let us look at another example. F of x equal to 1 divided by x. In this particular case, the curve looks like this. Okay, it's a hyperbolic type of a curve, and essentially when x is very close to 0 on the positive side, we will reach. So, for example, if x is 0.001, we reach plus infinity. When x is going to be equal to 0.00 minus 0.001, we will reach minus 1000, and as we go closer and closer to the y axis, we will go towards infinity. Now this particular example does not have any solution because this curve does not intersect the x axis except essentially at infinity. Okay. However, if we are going to use a bracketing method, especially a bracketing method such as the bisection method, these two are going to be admissible solutions. This is going to be our XL because, and this one is going to be our XR. The reason is the product f of XL multiplied by f of XR is going to be negative, so these are going to be our admissible solutions. So eventually, as we reduce this so the next point is perhaps going to be over here. This is going to be our new XR, then the next point will end up being over here. This is our new XL, this is going to be our new XL, and so on and so forth, and we will eventually reach the origin. As we approach the origin, what we will find is that f of XL tends to minus infinity, f of XR tends to plus infinity. So although the solution does not exist for this particular problem, we will be able to figure out that this particular curve has a discontinuity close to that at the particular point at 0, whereas such properties of the curves we will not be able to obtain using any of the open methods that we look at. This is kind of a cheating a little bit, because in this particular example we know a priori that the solution does not exist, and we are tricking our problem, and we are essentially making a trick to say that a bisection type of a method is able to figure out that the solution does not exist, whereas a method like say a secant method or the Newton-Raphson methods or the other methods that we are going to consider here, those methods will not be able to figure out that the solution does not exist for this particular problem. Okay, so this is in general about bracketing and open methods, and specifically about the secant method. The next method that we are going to consider is going to be fixed point iteration. Okay, the fixed point iteration method is will be used to solve any general problem of the form x equal to g of x. Okay, this is nothing but recasting of the original problem in this particular form. If this problem we were to write down as 0 equal to g of x minus x, this guy becomes our f of x, and f of x equal to 0 is going to be the form that we have looked at so far. Okay. Now the question is whether x equal to g of x is going to be unique, and the answer of course is no. If we look at the previous the example that we have been looking at in this particular module, that was 2 minus x plus ln of x equal to 0. One way we can write this as x is equal to 2 plus ln x. In that particular case, this becomes our g of x. The other way to write this this as is ln of x is going to be equal to x minus 2, or x is going to be e to the power x minus 2. Okay. So this is going to be the other possibility of g of x. Okay. So x equal to 2 plus ln x is also is also one way of writing this, and this is also the other way of writing this. So there is nothing unique about which way we can choose in order to write this particular expression. Okay. So now what do we do in the fixed point iteration is as follows. We will use that particular equation as an update equation. So first point is start with one initial guess, okay. We will write x I plus 1 equal to nothing but g of x I. I will use this left facing arrow to signify that the value computed as g of x I is going to be assigned to to x I plus 1. Okay. So we start with initial guess, we use g of x of I and assign it to x I plus 1, verify whether x I plus 1 minus x I is less than epsilon. If it is, indeed the solution is reached. If it is not, the solution is not reached, and we keep continuing this particular method over and over again. One of the problems actually with the fixed point iteration method is that it is not guaranteed to converge under all conditions. Oftentimes we will encounter a situation in which x I plus 1 keeps diverging away from the solution as as we try to solve this particular problem. What we will do is we will just now look at again use Excel in order to look at how the fixed point iteration is going to work, and then we will look at essentially the graphical interpretation of the fixed point iteration method. Okay. Okay. So far what we have done in the previous lecture and this lecture is looked at the bisection method, regular-Falsy method, and the secant method. All of these methods essentially used two initial guesses as the for finding the solution. Now we will go to fixed point iteration. Fixed point iteration method works essentially with only one initial guess, and let us just increase the sizes over here, yes, and we will also increase the font size so that it is easier for all of you guys to see. And the problem that we are interested to solve is the same problem as before. Okay, so we will just copy this. Okay. So this is the problem that we are interested in solving, and we will solve it in two different ways. I will call those two ways as fixed point iteration 1 and fixed point iteration 2. So we will just format the cells and merge the cells, and we have fixed point iteration 1, sorry, that should be fixed point iteration 1, and copy this and call this as fixed point iteration number 2. Okay. The difference between fixed point iteration 1 and fixed point iteration 2 is, what we will do is, in fixed point iteration 1 is take minus x to the right hand side and write this equation as x equal to 2 plus ln of x. So, we will write this equation as x equal to 2 plus ln of x. Okay. So, that is the way we are going to do the first fixed point iteration, and the second fixed point iteration I will just insert one row over here, so that it is clearer to visualize. In the second fixed point iteration, we take 2 minus x on to the right hand side and take the overall exponent of that. So, we will get x equal to e to the power x minus 2. So, this we can write it as ln of x is going to be equal to x minus 2, right. So, we have taken x minus 2 on to the right hand side, and now we take an exponent, and that will give us essentially x equal to e to the power x minus 2. Okay, and we will write this as e xp, exponent of x plus 2, and just change the font to our favorite Times New Roman, so that it is easier to see. Okay. So, the two ways of solving using the fixed point iteration is, one to write this particular equation as x equal to 2 plus ln x, other is to write that equation as x equal to exponent of x minus 2. Okay. And the same way as before, iteration, the initial guess is x of I, g of x of I, okay, and x of I will, let us say we will start off with 4 over here. G of x of I is going to be nothing but 2 plus ln of x of I, okay, and this is what we get. At the second iteration, x of I plus 1 is nothing but g of x of I. So, this is going to be equal to this guy, and as you see, implementation of fixed point iteration is so much simpler in Excel compared to any of the other methods, and that is all we need essentially. We do not need anything else, and we just keep dragging it, maybe let us say up to say 15 iterations, and we will also plot the error, okay, and the error is nothing but absolute value of the difference between the current solution and the previous solution, okay. And our stopping criterion is essentially where the overall error ends up being less than 10 to the power minus 4. 10 to the power minus 4 was the tolerance value that we had used, and as before we will just highlight the final solution over here. So, the final solution again we get is 3.1462. Keep in mind that the various solutions that we have gotten from say the secant method is again 3.14619. Since our error criterion was 10 to the power minus 4, it is essentially up to that particular digit that we can be confident of the solution, not to the digit after that. So, we can confidently say that the solution is in fact 3.1462, we cannot say anything about the last digit in that solution, and that is what if we just keep comparing with all the other methods, that is what we will see 6.1462, 6.1462, 6.1462 and 6.1462 is what we get as the solution using all of these methods, okay. So, this was one way of essentially using the fixed point iteration. Now, let us look at what happens if we start with, let us say, a very large value 10. If we start with a very large value for fixed point iteration, we are able to again converge to that same solution 3.1462. Let us say we start with a value of say 2, again we find that when we start with value of 2 we have reached again 3.146. Let us say what happens when we start with a value of 1, again we reach the same value as 3.146, and what happens if we start with value of let us say 0.2, again we are reaching 3.146. So you see what is happening is that when we write down this solution as x equal to 2 plus ln x, no matter what initial guess we use for this particular method, we are getting our solution to essentially go to the value 3.1462. okay. That is one of the things that happens with fixed point iteration. Using the fixed point iteration in this particular form, we will not be able to get to the solution which we got. I think the other solution was 0.15, we will not be able to get to that solution. Even if we start at 0.1, what we will get an error. So I have written this as 0.1 and I click enter and I get an error. The reason why I get an error essentially is that the next guess of xi plus 1 is a negative value, and log of a negative value is not defined. Okay, so let us go back to where we started off with. We started off with the initial guess of xi equal to 4, and with the guess of xi equal to 4 we get the convergence in 10 iterations. Okay, so that was the fixed point iteration number 1 using x equal to g of x written like this. The other possibility to write x equal to g of x is to write it in this particular form. In this case g of x is e to the power x minus 2. Okay, we will start with xi equal to 4 and see what happens with gi. Gi is nothing but exp of x minus 2. Okay, and that is the value that we get over here. At the second iteration, xi plus 1 equal to g of x of I. Okay, and then gi plus 1 we can just drag that over here, and error is nothing but absolute value of the difference. Okay, so this is what we have, and all we need to do is drag it, and let us drag it again for 15 iterations, and again you will see something funny that is happening as soon as I release the mouse button. And what happens is this, is if we start with an initial guess xi equal to 4, I will end up diverging. So this what we get is we get our x guess to go towards infinity, 10 to the power 20, we started with 4, from 4 we went to 7, from 7 we went to 219, from 219 we went to 1e94, and essentially from 1e94 we would have gone to infinity. Okay, that is what happens if you start with a poor initial guess like 4 in this particular case. Let us see what happens if we half this particular value from 4 to 2, and this is what we get. So we start with xi equal to 2, we go to gi equal to 1, from 1 we go to 0.36, so on and so forth, and we reach the other solution. So starting with xi equal to 2, again we are reaching the other solution and not this particular solution. Let us start with xi equal to 3 and see where we get. Again with xi equal to 3 we are getting to the solution 0.15. In fact, if we start with xi very close to the solution, let us say 3.14, even in the case when we started with 3.14, which was very close to the true solution 3.146, what we find over here is that our solution still goes to the other solution 0.1586. So in the fixed point iteration, using x equal to e to the power x minus 2 converges to the solution 0.1587 and not to the solution 3.1462, no matter how close to 3.1462 we start. Okay, and if we start with say 3.2, we will diverge. So if we start beyond the second solution, our fixed point iteration is diverging using x equal to e to the power x minus 2. Okay, so just to finish this off, starting with xi equal to 1, our stopping criterion is that the error should fall below 10 to the power minus 4. So, this is going to be our solution 0.1586. So, that is the solution using fixed point iteration, the method 2. What we just saw is essentially that the fixed point iteration, under certain conditions it converges to the solution, under certain other conditions the fixed point iteration is not going to converge to the solution. The particular problem was chosen such that we will not have big problems with the fixed point iteration method. In the next lecture what we will do is we will cover essentially how the fixed point iteration converges and under what conditions is the fixed point iteration not going to converge. Now what we will go on to is the next example, the next numerical technique for solving nonlinear algebraic equation, and that numerical technique is known as the Newton-Raphson method. Newton-Raphson method is arguably the most popular technique for solving nonlinear algebraic equations. The reason for its popularity we will cover in the next lecture. It's essentially gotten to do with its properties of convergence. The biggest reason for its popularity of course is because it's easily extendable to multiple dimensions. So the final method that we are going to cover in algebraic equation solving is the Newton-Raphson method. Okay. So again we are interested in solving f of x equal to 0, and in the Newton-Raphson method what we do is essentially we look at the curve. So this is what we did in the secant method, is we had for example 2 points and we connected those 2 points by a straight line. The point at which that particular straight line intersected the x axis is what our new guess essentially was. So this was our xi plus 1, or rather let us say this was our x2, okay. Then x2 and x1 we connected with a straight line again, and where x2 and x1 we connected with a straight line, and this became our x3. Then x3 and x2 we connected with a straight line, and this became our x4. So what happened in secant method is x2, x3, x4 when we started doing that, they started coming closer and closer to each other. So so let's consider the case where x2 and x3 are going to be very close to each other. So this particular line segment that joins x2 and x3 is nothing but a slope of the curve close to the point x3. So the question that we ask ourselves is, instead of calculating the slope of the curve by using the previous solution x2 and the current solution x3, what else can we do in order to get the slope of that curve? And the straightforward answer, what else we can do to get the slope of the curve, is nothing but its first differential with respect to x. So that is what we do essentially in the Newton-Raphson method. So what happens in the Newton-Raphson method is we do not start with two solutions, but just like fixed point iteration we will start with only one solution, okay. So let us say this sorry, not one solution, we start with one initial guess. This is our x1, we will obtain the tangent to the curve at point x1 and draw that particular line and find the point at which the tangent intersects the x axis. That particular point is our x2. At f of x2 again we find a tangent to that curve, find where it intersects the x axis, that becomes our x3, so on and so forth, okay. So the what we obtain is essentially we find the slope of the curve at xi. The slope of the curve of xi is nothing but f dash of xi, Okay. So, the slope of the curve is f dash of xi, the line that passes through that particular point with this particular slope is nothing but y minus f of xi is going to be equal to f dash of xi multiplied by x minus xi. Okay. Again, this is the slope, this is a line with slope f dash of xi that passes through the point f of xi comma xi comma f of xi. Okay. So, at the point at which this particular line intersects the x axis is nothing but the point x I plus 1 comma 0. So, we substitute that in this particular equation, okay, and we will get minus f of xi equal to f dash of xi multiplied by x I plus 1 minus xi. Okay. So, we can divide throughout by f dash of xi, okay, and take xi on to the other side, and the resulting equation that we will get is xi plus 1 is going to be equal to xi minus f of xi divided by f dash of xi. Okay. So, this is how we are going to use Newton-Raphson's method to come up with the next solution xi plus 1. Okay. So, let us go to the algorithm that we developed for the fixed point iteration. We start with a single initial guess xi. In fixed point iteration, what we did was we assigned g of xi to xi plus 1. We are not going to do that in Newton-Raphson's. Instead, what we are going to do in Newton-Raphson's method is we are going to use this particular equation and assign it to xi plus 1. So, our xi plus 1 is going to be nothing but xi minus f of xi divided by f dash computed at xi. Verify if xi plus 1 minus xi is less than epsilon. If it is less than epsilon, it is the solution. If it is not less than epsilon, we will repeat it until we get convergence. So, this is going to be our algorithm for the Newton-Raphson's method. Okay, and the Newton-Raphson method, like the fixed point iteration method, will start with just one initial guess and not two initial guesses, and we will just increase the font size as before so that it becomes easy to view. Okay, so we wanted to solve this particular equation f of x equal to 0. So, we will write this is our f of x, and let us differentiate f of x and write this as f dash of x is going to be equal to. So, f dash of x is going to so f dash of ln of x is going to be 1 divided by x minus 1. And just make this Times New Roman. Okay. So, now for Newton-Raphson's method, we need f of x, we need f dash of x, and that's essentially what will be sufficient for us to start with our Newton-Raphson's method. And I will just write down Newton-Raphson W. Okay. So, iteration we have as before, we will have xi, fi and f dash I. We will have x of I, f of I and f dash of I. Okay, this is what we get. The iteration index will start with 1 and xi as before will start with 4, and f of I is nothing but 2 minus xi plus ln of xi. Okay, and f dash is nothing but 1 divided by xi minus 1. Okay, so this is our fi, this is our f dash of I. In the second iteration, our x of I plus 1, I will just write that down over here, that equation down, which we had just computed on the board. It is xi minus f of I divided by f dash of I. Okay, again the Newton-Raphson is also fairly simple to implement in a relatively simple one dimensional problem like this. So x of I is nothing, x of I plus 1 is nothing but x of I minus f of I divided by f dash of I. Okay, and so this is going to be our new solution. X of I plus 1, we will just drag this and we will drag this also in order to get fi and f dash of I, and then we will compute the error as well, and error is nothing but the absolute value of the difference. Okay, so this is the error, and now we are ready as before. We are now ready to just drag and drop that particular row. We will just take this and maybe we will drag it say for 10 iterations and see where we go. Okay, and we really did not need all these 10 iterations. We have reached our desired solution in essentially in just 4 iterations over here. Okay, all right. So we started off with x of I equal to 4, f of x of I we computed, f dash of x of I we computed, x of I plus 1 was equal to x of I minus f of I divided by f dash of I. This is how x of I plus 1 was computed. Again for x of I plus 1 we computed f, again we computed f dash, and from this again we kept computing x of I plus 1 each and every time for at each iteration, and we find that the solution converges, reaches the desired tolerance value of 10 to the power minus 4 in 4 iterations only. Okay, so what we can now do is just compare, go back and compare the number of iterations that various methods have taken. This particular problem I spent some time in order to select a problem which showed the kind of features that are expected from these numerical techniques. This problem shows those features. So bisection method, it took 15 iterations to get to the solution. Regular-Falsy and the secant method took 5 and 6 iterations respectively. The number of iterations required by Regular-Falsy and secant methods are usually approximately the same as each other, because the underlying method of solving the particular problem to get xi plus 1 is not very different between Regular-Falsy and secant method. Fixed point iteration again took about 10 iterations or 8 iterations in order to converge, whereas Newton-Raphson's took actually just 4 iterations to converge. In general, the speed of iteration, which we will cover in our next lecture, goes Newton-Raphson's is faster than secant or fixed point, which in turn is faster secant or Regular-Falsy, which in turn is better than fixed point, which is approximately equal to bisection. We will cover this aspect later on in our lectures, that this is what the speed of iteration follows. Newton-Raphson's is better than the secant method, which is better than the fixed point iteration method in the open the various open methods. Okay. So, this is essentially what we intend to cover using Excel. What we will do in the next lecture is cover some of the other aspects of so this is what we have done using Excel. We have covered bisection, reguli falsi, secant method, fixed point iteration method, and the Newton-Raphson method using Excel. The way we have tried to use Excel is to bring out some of the salient features of each of these methods that are going to be of interest to us in discussing these methods going forward. We will talk in the next lecture about what we mean by the speed of convergence, how the convergence happens for 3 of these methods. We will take up bisection method, the the bisection method, the fixed point iteration method, and the Newton-Raphson method, and try to analyze these 3 methods in the next lecture. What we have covered so far in our lectures is the single variable case of solving f of x equal to 0 using these 5 different methods.